I can say that it's a pleasure for me to introduce Jack Harris from Yale University, today's speaker. Jack is no stranger to the people in the CUA. He was a postdoc here for a few years, working on a project in my lab, along with a collaboration with Wolfgang Ketterle on creating a Bose condensate without any laser cooling at all. And a lot of the work that was done there actually started studying some of these more exotic atoms which are now being used today, things like erbium, thulium, the rare earths, and studying the collisional properties. But before that, Jack was at UC Santa Barbara with Ashelon, his PhD in real condensed matter physics. One of his most famous papers is magnetization measurements of magnetic two-dimensional electron gases. So that's world famous. Yes. So Jack went from there to here, and while he was here, he showed that he was both a fantastic mentor, but also an incredible teacher. I remember his first group meeting talk. Everybody was in awe at the clarity of, and simplicity of his explanations. I'll never forget that. He went with, at the same, did Andrew go with you, or did you recruit him later?
He came a year after me.
A year. So Jack went to Yale and took one of our undergraduates that was working in the lab, Andrew Jayich, who's now went westward. And Jack with Andrew did a number of pioneering experiments in the control and study of quantum mechanical properties of mechanical systems. And this was really very, very new at the time. There was a little bit of discussion about it, but I think it's very fair to say that Jack was one of the key pioneers. And out of that came a number of papers. I was planning on telling you the titles of those papers, but I'll just hand it over to Jack.
Thank you very much. Thanks, John, for the introduction. And you okay? Yes. Okay. Well, so it's a pleasure to be back here. It's a pleasure to be standing strangely at the front end of this room where I sat and listened to many talks over the years. And it's quite humbling to listen to all the amazing research work that's going on here that I got to hear about earlier today. So as John mentioned, the field that I'm going to be telling you about today is called optomechanics, and this is a field where we're interested in coupling the motion of relatively large, solid, macroscopic objects to the electromagnetic field, and in particular the electromagnetic field of optical cavities. The reason that we're interested in doing this is because it turns out that radiation pressure, the means by which massive macroscopic mechanical objects couple to light fields, provides a particularly powerful way for coaxing quantum mechanical effects out of the macroscopic objects, from transferring, if you will, quantum mechanical fluctuations of the light field into the motion of these large solid objects. So these are the topics that I'll be covering today, but everything that I'll be talking about hinges on the basic interaction of radiation pressure. And radiation pressure sometimes we encounter as a fanciful form of space travel in the solar sail, or in the little funny toy that you can buy that looks like a light bulb with a funny little windmill that is reported to spin around under the influence of radiation pressure. That's actually not why it spins around, but it turns out that radiation pressure actually has a long history in addressing fundamental questions in physics. So I will start with just a very brief overview of that development, and a very chauvinistic overview, maybe. The first theoretical elucidation of what my tiny little field would call optomechanics, which is the interaction of macroscopic solid objects with the light field, was provided by Maxwell in his original treatise on electricity and magnetism. Prior to this time, people had sort of intuited that maybe light would push against something, but in this sort of grand unified field theory of its day, Maxwell actually derived this from what we would now call the Maxwell equations. And if you read through this treatise, about 900 pages, this is certainly a masterpiece of theoretical physics, but maybe not of exposition. After 900 pages, you find this very clear statement that a traveling plane electromagnetic wave exerts a force that's equal to twice the incident power carried in the electromagnetic wave. Nowadays we would divide that by the speed of light. And that this is radiation pressure. Maxwell goes on to point out to provide some helpful hints to the experimentalists of the day. This is one of the important testable experimental predictions of this new theory. And so the goal of testing this experimentally by observing radiation pressure sparked an international race between experimentalists. Maxwell provides some helpful suggestions to them. He says, don't bother trying to measure the pressure due to sunlight. That will be very small. He says, you might want to take advantage of the exotic leading technologies of the day and focus the concentrated rays of the electric lamp. Helpful suggestion. This was taken to heart by the experimentalists, but it took another 30 years before radiation pressure could be measured accurately in the lab, more or less at the same time by Peter Lebedev in Russia and Ernst Fox-Nichols at Dartmouth, where they suspended by very fine wire a pair of mirrors and shown the concentrated rays of the electric lamp onto one of those mirrors and observed that the mechanical object was deflected in agreement with the predictions of Maxwell's classical theory of electricity and magnetism. What I want to talk about today is the same physics, but at the quantum mechanical level. And you might be justified in expecting that a quantum theory of this kind of phenomena would have to wait quite a few decades after the classical exposition. It should certainly wait at least for Schrodinger's equation or maybe even QED. But in fact, the dawn of what I would call quantum optomechanics occurs just a few years after these experiments. And that's in a paper in 1909 by Albert Einstein. I'd never read a paper by Einstein before, but reading this in translation anyway, absolutely made the hair on the back of my neck go up. It's a completely amazing paper in which, among other things, Einstein more or less lays out the program for quantum electrodynamics, for the quantum theory of the electromagnetic field and its interactions with the electron. He talks about the fine structure constant. The main point of the paper, though, at least for the purposes of this talk, is that he begins simply by taking seriously Planck's expression for a black body spectrum. And he uses very general arguments about statistical mechanics to say that if that's the state of the electromagnetic field that maximizes entropy, then we can also calculate from that spectrum the fluctuations of the field. So he calculates not just the energy in a certain frequency band, which Planck had provided, but he takes that formula and calculates the fluctuations of the energy in a given energy band. And at the same time, he says, well, it's no problem to convert this into a radiation pressure. We know that electromagnetic energy exerts a force, so fluctuating electromagnetic energy must exert a force that fluctuates. And this is his expression here. This is the variance of the flux of the radiation pressure derived directly from Maxwell's equations. And it comes up with two terms. This is basically just gotten by taking derivatives of the Planckian spectrum. One of them appears over here, and as he points out in the paper, this is just the fluctuating force that you would get if you took Maxwell's equations with all of the normal modes of the electromagnetic field and let each mode be driven by a thermal bath at temperature kT. All those modes would interfere in a funny way and they would add it like this. But you get a second term from Planck's expression, which involves the constant, the Planck's constant from Planck's expression. And Einstein points out that this is exactly what you would get if you were to instead imagine that this energy was contained in little particles, each of it containing energy, or let's say containing momentum of h bar k, rattling around at random. And this is the text from here. And this is the paper which, as I understand it, led Einstein to really take the concept of the photon seriously for the first time. So this is a phenomenon that in our little field today we would call the shot noise of radiation pressure, the fluctuations that are due to the fact that it's being exerted by the impact of little discrete objects. And schematically, this calculation states that if you have a glowing hot object, the black body radiation will exert a force on the mirror, but that force will actually have little pings in it and cause the mirror not just to be pushed, but to actually jiggle in place. So these are the three events that I described. The quantum aspects of radiation pressure, the idea that it was going to be exerted photon by photon, plays an important role in the famous debates between Bohr and Einstein about the interpretation of measurements in quantum mechanics. And from the point of view of our field, there's maybe a fallow period for a couple of decades until two important new avenues in research The first is the serious effort to detect astrophysical gravitational waves. And it was with the initial designs of these experiments that people began to think very carefully about what kind of limits would be imposed on an interferometer, given that the mirrors forming that interferometer are subject to the constant buffeting of colliding photons. Within that field, these questions were worked out in great detail and have resulted in real astrophysical gravitational wave detectors that are now approaching the limits imposed on them by the quantum mechanics of fluctuating radiation pressure. The other field that the work that I'll be describing draws on greatly is the field of cold atoms and optical trapping and laser cooling, where again the quantum fluctuations of radiation pressure sets limits, for example, to the lowest temperature that can be reached by laser cooling of cold atoms. And the work that I'll be describing today is really sort of at the interface between these two areas, where we take concepts and ideas and techniques from both of them, not with the goal of detecting astrophysical gravitational waves or colliding black holes, or with the goal of producing ultra-cold Bose-Einstein condensates, but simply studying the physics of how a solid object interacts with the quantum fluctuations of the electromagnetic field that it's in. So within this field, quantum mechanical effects were observed in these systems starting in about 2010. And since then, experiments have progressed rapidly. I would say that all of these quantum mechanical effects that have been observed in the motion of what we would call micromechanical oscillators fall into a particular category. They're quantum effects that are associated with Gaussian states. They're quantum effects that, if you simply refuse to believe in quantum mechanics, you could absolutely reproduce by coupling the relevant degrees of freedom to the appropriate thermal bath. There's nothing like a violation of a Bell inequality in these experiments with massive objects or negative Wigner functions, but rather the observations of things like zero-point fluctuations or measurement back action. So these are the sorts of phenomena that have been studied to date, and the results that I'll be talking about also fall squarely within this realm of Gaussian quantum states and Gaussian quantum effects. The future of the field, I think, is very much going beyond those limitations. There are a variety of directions that people are interested in exploring. Some of them have to do with making the optomechanical interaction strong enough that it would be possible to realize non-Gaussian quantum states. There are somewhat far-fetched but interesting ideas about testing whether or not gravitational field of an object that's placed in a superposition has a non-trivial impact on that object's motion. And I think there's some interesting physics to be studied in optomechanical systems in which the macroscopic degree of freedom isn't necessarily the normal mode of a solid, but maybe some other kind of degree of freedom, for example, associated with a fluid. So I'll touch on at least this a little bit towards the rest of my talk. So the field in which these phenomena are studied spans a very wide range of different experimental realizations. These are all optomechanics experiments looking at this physics. They range from the kilogram, kilometer scale experiments associated with gravitational waves all the way down to centimeter and millimeter and micron and nano-sized objects. And even though they have this very diverse realizations in the lab, all of these experiments are studying just one thing. The thing that they are studying is this. All of these experiments are just different ways of realizing a system in which you have a single mode of the electromagnetic field that is coupled to the motion of something. So you can think about that conceptually as a Fabry-Perot cavity with its mode defined as a standing wave in there that is detuned, that is affected in some way by the displacement of one of the end mirrors of the Fabry-Perot cavity. It could as well be the deformation of a whispering gallery mode resonator or any other kind of motion. But this is the toy model that all of these experiments realize. So the Hamiltonian for this system is relatively simple to write down. It's just two harmonic oscillators, the electromagnetic oscillator and the mechanical oscillator here, described by the photon creation operator A dagger and the phonon creation operator B dagger. And the only reason that they talk to each other at all is that the frequency of the optical mode depends upon the displacement of the mechanical degree of freedom. As long as we're talking about small motions, small values of x, we can Taylor expand this function to lowest order. The constant terms just leave us with the unperturbed optical resonator the unperturbed mechanical resonator, and then a coupling term in which I've just rewritten the displacement of the mechanical oscillator in terms of the phonon operators here. In this system, there are maybe two qualitatively different realms to consider. One is in which are set by the size of this coupling right here, G naught. G naught has units of hertz. Its physical meaning is just that this is the amount of hertz by which an optical cavity is detuned when the mechanical oscillator undergoes its zero-point motion. And so typically that's not a lot of hertz. In the experiments that I'll be describing, that's going to be about 1 hertz. If that frequency happens to be larger than some of the other important frequency scales in the system, such as kappa, the rate at which photons are being lost out of the optical system, or omega, the frequency of the mechanical oscillators, there's some very interesting physics. This would be the strong coupling or single quantum strong coupling regime of optomechanics, a regime that hasn't been accessed to date in experiments. Instead, what I'll be talking about are experiments in which G naught is much smaller than either of these quantities, but that's compensated for by the fact that we put an awful lot of photons inside the cavity. And the fluctuation of this large population of photons, quantum fluctuations, is hopefully going to be enough to have some discernible impact on the motion of this object here. Okay. So let me explain how such an experiment works and where you would begin to look for quantum mechanical effects. To do that, this is maybe a little more introductory than is absolutely necessary, but let me just illustrate it in the following way. Suppose I have a mirror and I shine green light on it. The light that comes back is still green. Its spectrum is illustrated here. If, on the other hand, this mirror is free to oscillate, if it's a harmonic oscillator with some resonant frequency, then light undergoing reflection has some other options. It could absorb a quantum of energy out of this oscillator and as a result come out a bit blue shifted. It could deposit a quantum of energy in this mechanical oscillator and losing that energy come out a bit to the red. And so the spectrum of reflected light would be as illustrated here. In the experiments that I'm going to be talking about, we put a cavity around this system which modifies the density of states, density of states for the light to scatter into. That's not super important at this point. The place that we begin to look at for quantum mechanical effects has to do with the relative rates of these two processes. This is not a 100% accurate description of the underlying physics, but as a first pass, you could note that the emission of a red photon involves the depositing of energy in the mechanical oscillator. When you raise an oscillator, you acquire a matrix element that's like square root of that oscillator's quantum number, phonon number plus 1. And so the rate here, the square of the matrix element, will be proportional to the mean phonon number plus 1. Whereas the anti-Stokes process, the emission of blue light, involves the extraction of a quantum of energy, the lowering of the mechanical oscillator, and so involves a rate that's proportional just to the oscillator's phonon number. So this is the interpretation of sideband asymmetry that's often applied in ion trapping type of experiments. It's not really an accurate description of what the experiments that I'll be talking about here for the following reason. When we do experiments, we are not simply going to have a detector that just counts red photons and having counted them has some impact on the phonon number of the mechanical oscillator. In order to actually measure these sidebands, we send a local oscillator into the system, and we, in the photocurrent, we see a beat note at this frequency, which is our intensity of the red sideband. We see a beat note at this frequency, which is the intensity of the blue sideband. And as far as the photodiode is concerned, it's just a wash in photons, most of which are unshifted photons from the local oscillator or the probe beam and not associated with raising or lowering of the mechanical oscillator. As a result of that, the interpretation of these sidebands is a little bit different. I can walk you through that very briefly here. This is the same cartoon. If I calculate the photocurrent produced at this diode, it has 4 different components. One is simply the shot noise of the laser light falling on the photodiode and being converted into current. There's a second contribution, which is due to the zero-point motion of the mechanical oscillator. So this would be for example, with the oscillator at zero temperature and describing the system within a quantum Langevin approach, the oscillator zero-point motion puts frequency modulation sidebands, if you will, on the light coming out, leading to sidebands at the detector. At the same time, the mechanical oscillator is subject to the quantum fluctuations of the radiation pressure. Those fluctuations cause the oscillator to move. That motion, again, imprints just more frequency modulation sidebands on the outgoing light, but those fluctuations are not independent of the fluctuations that are producing the shot noise at the photodetector, with the results that the oscillator's motion produces a sideband that adds to the contribution from its zero-point motion on the red side, but cancels it on the blue side, with the net results that in its ground state you would expect to see a certain amount of motion, a certain amount of signal on the red sideband and none on the blue sideband. Qualitatively, this is the exact same kind of signal that we would expect in an ion trapping kind of experiment. A signal on the red side that's photon number +1, a signal on the blue side that's just the photon number, but the underlying physics is different. So that's the manner in which the quantum behavior of the electromagnetic field and of the oscillator is going to manifest itself. The next question to address is simply the one of scale. So the oscillators that we're going to be talking about are sort of megahertz oscillators. And so at room temperature, have a typical photon number of 10 to the 7. In principle, if you measured the sidebands very, very precisely, you could see a difference between them. But in practice, that's rather hopeless, as would be measuring at the sort of the base temperatures of the kind of cryostats that we would be using. If you're interested in this quantum mechanical behavior, it would really be ideal to have the oscillator cooled more or less to its ground state, which is 30 microkelvin. That's not accessible with conventional cryogenics. But if you could do that, the asymmetry between the two sidebands would be much easier to notice. In order to access these very low temperatures, we're going to make use of very similar physics to what I described to you before. We're going to have one laser that is carrying out the measurement that I just described to you. But the second laser beam is going to be addressing a completely separate mode of the cavity, a different longitudinal mode, with a detuning relative to that cavity resonance. The point being that as this light experiences Stokes and anti-Stokes scattering, the density of states created by the optical cavity will tend to favor one of those processes over the other. And as I've illustrated here, the process that's favored is the process that involves the continuous extraction of energy from the mechanical oscillator. So simply by shining this light at the appropriate detuning, energy will be removed from the mechanical oscillator via blue-shifted photons coming out. This will provide the low temperatures that we're interested in. It's important to note that what I just described to you is just a form of damping. There's a process that I turn on that tends to suck energy out of this mechanical oscillator. And one nice thing about it is that, at least in the simplest picture, the cooling and the damping are exactly the same phenomena, which provides us with at least one simple way of estimating the temperature of the oscillator. Just the ratio, by the factor by which it is cooled, should be the same as the factor by which the damping is increased. Okay, so that's sort of the basic introduction to the physics that will be after. Any questions? All right, so the experiments that I will describe, just like all the others, realize this funny little cartoon. In practice, what we do is we build a perfectly rigid Fabry-Perot cavity, and then our mechanical oscillator is a thin sheet of dielectric that we place inside the standing wave. As it wiggles back and forth, it causes the cavity to detune. It's the exact same physics as described here. It's just technically a bit more convenient. The experiment looks like this. We take these silicon nitride membranes, which are a square millimeter and about 100 nanometers thick. They're mounted on a little stage. This titanium stage gets slipped into a titanium spacer, which forms the Fabry-Perot cavity. There's a high finesse mirror here, and on the other side, the membrane is sitting in between where the photons are going to be bouncing back and forth. All of this gets mounted inside of a helium-3 refrigerator. This is a few centimeters here. The system is rather unwieldy. There's a lot of in situ alignment that has to be done at low temperatures, a lot of careful vibration isolation. But once it's working, it behaves fairly well. This did take a lot of years, though, to work out technical bugs. This is a schematic of the laser setup. There really are two distinct lasers. One of them is going to be doing that measurement that I described, driving one mode on resonance and producing sidebands that will be monitoring. A completely separate laser is used to provide the laser cooling. The mechanical oscillator resonance at about 700 kilohertz. It's a square millimeter with a mass of maybe 40 nanograms. The cavity finesse is about 40,000, which means that each photon, on average, bounces back and forth about 40,000 times before leaking out or being lost somehow. So when we make measurements of these two sidebands, this is an example of the recorded photocurrent spectrum. This is the contribution from the red sideband. This is the contribution from the blue sideband. There's a huge peak somewhere in the middle. It's the beating between the local oscillator and the unscattered light, but we filter that out one way or the other. Recording the photocurrent spectrum is relatively simple. In order to convert it to an inferred motion of the mechanical oscillator, we go through a lot of calibration measurements, measuring the cavity's line width and its inputs, coupling efficiency, all the detector efficiencies. These calibration measurements allow us to turn the photocurrent record into a displacement record. To extract the information that we're interested in, we fit data like this to 2 to 6 parameters. The resonant frequency of the mechanical oscillator, which sets the location of these peaks. The damping, which sets the damping of the width of both peaks. The noise floor down here, which is going to tell us something about our detector gains and detection efficiencies. And then just the size of each of these sidebands. And we'll use these fits to infer the photon number in various ways. So this is an example of the kind of data that we take. This is a record of those red sidebands and blue sidebands as we're gradually cranking up the power of the cooling laser. The measurement laser is left completely constant. We're just gradually turning up the cooling laser power to provide more and more damping, and at the same time more and more cooling of the mechanical motion. So what you can see here is that damping. The motion gets damped and damped and damped. It gets smaller and smaller and smaller in amplitude. Over here I'm showing just more data, and now for the first time I'm adding a little offset to each data set just to keep things clear. The bold numbers here indicate the inferred number of phonons left in the mechanical oscillator. I'll tell you in a minute about how we actually extract that. But qualitatively what you can see is what was advertised. The mechanical motion gets an awful lot smaller, and it gets more damped as expected by the cooling mechanism. In addition, at the very lowest temperatures, you can see a clear asymmetry between the sideband on the red side and the sideband on the blue side, which gets smaller. To show that more clearly, here I'm taking the two data sets, the red sideband and blue sideband, and just flipping them on top of each other. So for the 10 phonon, the data here with about 10 phonons, the data with about 4 phonons here, with about 2 phonons, and with less than 1 phonon. And the size of this asymmetry, the difference is constant, but it becomes a larger and larger fraction of the overall signal as the phonon number is lowered. So this is the scaling of the blue signal with the number of phonons, and the scaling of the red signal with the number of phonons plus 1. So I should say that these kinds of measurements aren't foolproof. There are a lot, this is not some sort of dramatic striking effect, like a bigger function that suddenly has to be negative somewhere. This is, you're measuring two signals and one of them got smaller than the other. So there are a lot of careful steps in ensuring that this isn't due to some kind of artifact, and I'll just describe some of those to you briefly now. So there are multiple ways to take data like this and infer the phonon number of the oscillator from it. The simplest way is just to use this simple fact that I described to you before, that if everything about the experiment is very well behaved, you just expect the red sideband and the blue sideband to have a ratio that's phonon number plus 1 over phonon number. So if you just take the data for this ratio and invert it for phonon number, here's that asymmetry plotted as a function of cooling laser power. This would be the phonon number that you extract from that just difference in sideband. The nice thing about this is it doesn't really matter what our absolute calibration is. Absolute calibrations of the total signal go away when you take this ratio, but these kinds of interpretation is definitely susceptible to a different gain in your microwave amplifier at the frequency where the red sideband is coming out and the frequency where the blue sideband is coming out. So in order to get a completely independent, almost, a very independent measurement of the phonon number, we can look at a completely different quantity, which is the mechanical oscillator's line width, the damping rate of the oscillator. Just based on totally classical physics, as I crank up the cooling power and lower its temperature, I should be damping it by exactly the same factor. So from this measurement of mechanical line width, which is just fitting a Lorentzian, it's very simple. The error, I would say foolproof, but somehow that I'm not sure who I'd be insulting. Mechanical oscillator's Q by a certain fraction, you're lowering its temperature by the exact same fraction. So all we need to do, knowing the oscillator's original Q, is to know its original bath temperature, and then turn this damping amount into a phonon number. So all we have to do is to know the bath temperature of the oscillator. So here's a measurement of the oscillator's bath temperature. So there's an old saying in low temperature physics that if you have one thermometer, you know your temperature, but if you have two thermometers, you never know your temperature. It's not quite that bad. These are two very different thermometers. One of them is bolted right to our refrigerator. The other one is bolted to a piece of metal that is near the silicon oscillator. We just don't have a way of gluing a thermometer right to the silicon oscillator. What we say is, look, let's assume that the silicon oscillator is just at some average of these two temperatures, some weighted average between the two, and let the weighting of that average be our one fitting parameter. So the weighting of these two guys is going to take all of this data and plop it on here with just some scale factor that's being set by the averaging ratio. When we do that, the best fit, the best choice for the scaling factor is pretty much just a plain average between these two thermometers. And when we take that, the best fit lays this damping data, the temperature inferred from the damping, and then converted to a phonon number right on top of the values of the phonon number inferred from this purely quantum mechanical effect of sideband asymmetry. These aren't the only two pieces of information that we have, though. We also tried to do a really careful calibration of how much the oscillators seem to be wiggling. And if you believe in equipartition theorem, we can just take the amount of motion, the area under the sideband, and use equipartition to convert that into a temperature, and from that a phonon number. This approach requires us to do our calibration carefully, but if we just take the areas of the blue sideband, this is the inferred phonon number. The area of the red sideband also should obey equipartition, but the conversion is a little bit different. It has this n+1 factor here, which is why the area stops getting smaller as we cool it more and more. This is what I showed you qualitatively on the previous slide. So if we apply the appropriate equipartition expression to the data from the red sideband, again it agrees pretty well. If we just take all of the parameters that we've measured of the device, its mechanical Q, the cavity line width, the temperature of the bath, and turn that into a prediction for the phonon number of the oscillator as a function of cooling power, it's this black line here. So between all of these data sets, we have a pretty clear picture of a mechanical oscillator that's being cooled to just under 1 phonon, and which is showing this sideband asymmetry that's related to the quantum fluctuations of the electromagnetic field in the cavity and the zero-point motion of the mechanical oscillator. So that's what I've quickly listed up here. Laser cooling to a phonon number just under 1, and the sideband asymmetry related to the quantum aspects of the device. And I should say that all of this physics has been studied, measurements very much like this have been carried out in optomechanical devices already. Some of the devices shown in that rogues gallery of images have shown just more or less exactly the same effect. What is new to this work is that we've really gone through those 4 separate measurements, somewhat independent measurements, that they all agree very well with each other. There's some technical niceties associated with the experiment, but maybe the biggest difference is just the physical scale of the object that we're talking about. So here it is, this 1 millimeter sized object. What we've done is we've taken one of its low order drumhead modes, and we've taken only that mode and cooled it to its ground state. Exact same results were achieved by groups at Boulder, at Caltech, Santa Barbara, and another group at Caltech with devices that look like this. But to give a sense of the difference in physical scale, if I draw a little cartoon shape on top of the mechanical oscillator of each of these, and then replot them on the same scale, this is how big they are. So it's just a much, much larger object, showing exactly the same kind of simple cavity QED type of physics. Okay. So I should mention that very similar physics was also studied in a very similar device in Cindy Riegel's group at Gilla. Their device was sort of almost as big as ours and showed very similar effects. So we're in good company. And again, all of this quantum mechanics underlying this is the quantum mechanics of Gaussian states, It's just fluctuations that, according to classical mechanics, wouldn't be there if things were really, really cold. So more ambitious goals in the quantum mechanics of massive macroscopic objects are ahead of us, but they really require access to this single quantum strong coupling. So that's what I'm going to say about the membrane in the middle setup. The remainder of the time, I'm going to tell you about a second experiment that began as an effort to address some of the technical nightmares that are associated with this experiment. So the experiment that I told you about makes for very pretty computer graphic cartoons. Like this is what we would like the experiment to look like. In reality, it's much harder. There's a lot of alignment that has to be done in situ at cryogenic temperatures with sort of sub-nanometer precision. In addition, the mechanical oscillator that we want to be cold is this very insulating, skinny, long, horrible aspect ratio thing that in no way is thermally linked in a nice way to the cold point of the dilution refrigerator. We do the best job we can with little copper wires and stuff, but it's just not a natural arrangement. What we would like is something more akin to what would be studied in condensed matter physics, where the device would just be a little thing that we would bolt onto the cold point of the dilution refrigerator. We would run one wire, maybe two, out of the fridge. We would plug it into our equipment rack. We would do our measurements, and that would be it. No mechanical alignment. So this is an artist's conception of what we would like. And in order to realize this, we've been leveraging a very beautiful technique developed by Jakob Reichel at the ENS, where he takes a single-mode optical fiber, chops it off, zaps the face once with a CO2 laser, that blows off a bit of glass, leaving behind a little crater coated in hot, boiling hot molten glass. In about a nanosecond, surface tension makes that liquid get very, very smooth, and in another nanosecond, it solidifies and turns back into glass. And it leaves surfaces that look like this in an interferometer or like this in an SEM. If you go in with an atomic force microscope, they have a surface roughness that's equivalent to the best super polish you could get on macroscopic glass. And as a result, you can send it off to the fancy coating company. They will deposit a high finesse mirror on it. And then you take two of these fibers and point them at each other. And this is really where the wonderful thing happens. The concavity that you blew in the surface gives you a stable resonator. The mirror gives you high finesse. And the confined mode between them actually has pretty good coupling to the traveling mode inside the fiber. So this means that for the first time you have a fiber-coupled cavity with no input optics to align whatsoever. Operating at telecom wavelengths with all the sort of niceties associated with that. What we found in our lab was that you could take two of these fibers and a precision-machined glass ferrule, which are mass-produced for the telecom industry. They cost about $1 each. And you take this glass rod with a hole drilled through it, you slide one of these fibers in from one side, the other in from the other side, and you bump them into each other. And then you pull them back a tiny bit, and you have a high finesse cavity. And that's it, perfectly aligned, fiber coupled. All you have to do is take those fibers and connectorize them and connect them to your equipment rack. And you get the high finesse cavity in here. The problem is that it's an incredibly boring object, because there's nothing inside this cavity. It's just an empty, simple harmonic oscillator in the electromagnetic field. So Jakob's group drops cold atoms in there. They do beautiful things with it. Our idea was to take this device, and in order to get a mechanical oscillator in there, dunk it into a bucket of liquid helium. The idea being that the superfluid helium would creep in, fill up this volume, and provide us with our mechanical oscillator. And the point of this mechanical oscillator is the following. The mechanical oscillator is nothing other than the sound waves in liquid helium. And when I first was thinking about this, I thought, oh no, I'm going to have to finally understand what second sound is. An entire career devoted to not understanding this physics was going to be chucked under the wheels. But it turns out that at sufficiently low temperatures, where there's no normal fluid, liquid helium is just a pure superfluid. It's just one material. And then I thought, oh no, I'm going to have to learn about the Navier-Stokes equation. No. It turns out that if you linearize the Navier-Stokes equation appropriately, only very small, each volume element is only allowed to stretch a tiny bit. There's no rotational flow or anything like that. The Navier-Stokes equation reduces to just the plain old wave equation. So superfluid liquid helium is just a linear acoustic medium with density waves propagating. So that's nice. The thing that we really liked about this is that if you think about density waves whose wavelength is, say, approximately the wavelength of the light, they're going to satisfy exactly the same kind of paraxial relationship. And so these mirror surfaces here that confine the light wave and give you a high finesse cavity, and that are a bit curved to give you nice Gaussian beams that don't leak out or do anything funny like that. The exact same statement is going to apply to the sound waves. The sound waves are also going to be confined into little Gaussian modes that live inside this cavity and occupy exactly the same volume as the electromagnetic fields of the cavity. So there's no alignment whatsoever to do. The acoustic modes are perfectly aligned with the optical modes right from the get-go. So do they couple to each other, the light and the acoustic degree of freedom? They do, and it's a very simple form. If you look at the intensity of a standing wave inside of the cavity, this is the second optical mode inside of the cavity, and this is its intensity. And then I think about the density of liquid helium that's associated with one of the sound waves of liquid helium. Here's this density standing wave of the fourth wavelength. You can see that there's a nice thing going on. Wherever the light is, at the antinodes of the optical field, the liquid helium isn't. It has all sloshed over to the nodes. The liquid helium in this picture has sloshed over to the nodes of the field. And so as far as the light is concerned, there's less helium in there than there would be normally. Half a period of the mechanical oscillation later, this helium has sloshed back over here and is now sitting on top of the optical antinodes. And as far as the light is concerned, there's too much helium. All that the light knows about is the optical length of the cavity. So as far as the light is concerned, the index of refraction is being modulated. That's the same thing as the cavity getting longer and shorter. So this is now just our regular old optomechanics. It's a cavity that gets longer and shorter as the result of some oscillator oscillating. Every other sound wave, though, is perfectly orthogonal to this intensity wave and so has no coupling. This is the same thing if you used to stimulated Brillouin scattering. This is the Brillouin scattering condition. So if you send in light at 1550 nanometers, it couples to sound waves with half that wavelength, which, given the speed of sound in liquid helium, is a 315 megahertz frequency. And so it's the usual old optomechanics with the usual old coupling. The nice thing is that if you just do the 3D modes overlap integral between the acoustic mode and the optical mode, you get single quantum coupling rates that are in the kilohertz now instead of the hertz. So that's a very nice addition, as well as all the other things that I mentioned. So the device really works. They're in fact so straightforward to build that we just put 3 of them in the same device. This is a glass ferrule, a fiber coming in from this side, a fiber coming in from this side. Here's another one, here's another one. They live inside this little brass can that's connected to a capillary line that we can fill with liquid helium. It lives down here. This is a complicated looking cryogenic apparatus, but unlike the other one, none of this, there's no vibration isolation in here. There's no translation stages. There's no funny little hundreds of copper wires being glued and clamped in various places. We just bolt this little brass can to the cold point of the dilution refrigerator. Light comes in on an optical fiber, goes back out on the optical fiber. And the same thing with liquid helium, just down a plumbing line. So this shows that the optical cavity is not spoiled by filling the thing with liquid helium. This is data taken at the base temperature of the dilution refrigerator. The red line is the optical cavity before we fill it with liquid helium. The blue is after we've put the liquid helium in. We wouldn't expect photons to be gobbled up by liquid helium. It has the largest band gap of any condensed material in the universe, as far as I know. It's 20 electron volt band gap, no impurities, but it's still nice to see this actually happen in reality. That you can take a high finesse cavity, fill it with superfluid helium, and nothing bad happens. So now we'd like to characterize the optomechanical coupling. I won't go into detail about how we do this, but it's just a bit inconvenient. The way we do this is the following. We would like to see that the light is somehow pushing on this acoustic mode, that it's pushing on the density wave of the helium. So to make that happen, we send in one laser beam to the cavity, and then we send in another laser beam whose frequency we can vary. The result is that there's an intensity beat note inside the cavity. And if that intensity beat note just lines up with the natural resonant frequency of the acoustics, it'll excite it. Otherwise, it doesn't really do anything. So that's all this animation here. And here's that data. So this is monitoring the reflected light as we vary the beat note frequency between these two beams. And as we sweep that beat note frequency over 314 megahertz, you see this very sharp resonance. This is the excitation of the first sound wave within liquid helium. By fitting this kind of data, this kind of measurement is called optomechanically induced transparency. in homage to the EIT studies in other systems. By fitting that kind of data, as we take those two beams and detune them with respect to the cavity line, we monitor the size of those peaks as well as their phase. And by fitting them, we can extract the size of this optomechanical coupling. It is indeed about 3 kilohertz as expected from just doing the overlap integrals. This tells us that the coupling between the light waves and the acoustics is just electrostriction. It's just radiation pressure. It's just dipole forces. There's no funny heating that's going on and dominating this or any other means of excitation between the light and the acoustic waves. So just a couple more slides here. We find that the device does heat up a bit. Well, okay. What I want to tell you about now is the mechanical Q of this superfluid oscillator. It should be infinite because it's a superfluid. There's no viscosity, there's no damping. That would be wonderful if that was true. That's not really how it works. It is true that there's no viscosity in this fluid. Water would be much worse. But liquid helium, like any material, has a bit of anelasticity. And that means that if there's an excitation, if there's a phonon traveling through it, that phonon can spontaneously down-convert into other phonons. That looks like loss. It's not exactly the same thing necessarily, but it's close enough. So that process is very well understood in liquid helium. It depends on temperature like T to the 4th. And you can see that as we cool the device down, yes, the Q does get better and better and better until it stops getting better. Why is it stopping to get better? Well, the only reason that sound is confined in the liquid helium at all is just because there's an impedance mismatch between liquid helium and glass. The fancy coating that gives us our high finesse optical cavity doesn't do anything for the sound waves, just the wrong wavelengths. Nevertheless, that is about the world's biggest impedance mismatch you could imagine. Sound in superfluid helium to sound in glass. So there's pretty good reflectivity there, but just the ability of sound waves to leak back into the optical fiber is going to limit the mechanical quality factor to 60,000 or so. In addition, as we crank up the power incident on the cavity, we see that the mechanical Q also gets worse. It turns out that this is just the mimicking of the temperature dependence. The device is heating up a bit. If we take a simple thermal model for how much the device is heated up and how well it's thermally anchored to the mixing chamber, all of this data collapses on a single curve, and the red line is the known mechanical anelasticity of liquid helium. The blue line is the expected radiation of sound waves back into the glass. So this makes pretty good sense. So from this, we can see that we understand what the thermodynamic temperature of the liquid helium, what the material temperature of it is. It's getting down to about 100 millikelvin. What we'd like to know now is, does this mode of interest, this 315 megahertz, does its phonon number track this temperature, or is it getting anomalously heated or anomalously cooled? So to do that, we repeat the measurement that I told you about back in the membranes. We just monitor the thermal fluctuations of the device. We don't drive it at all. We just have one laser beam, and the fluctuations of this acoustic mode will imprint some phase modulation on the beam. That's what we record here as we vary the temperature of the refrigerator and as we vary the temperature of the device by changing the amount of laser power incident on it. When I subtract off the noise floors of all this data, they lie on top of each other like this, and if we infer the phonon number from them, which is in this normalization just the height of each of these peaks, the inferred phonon number in this mode as a function of the device's temperature lies right on the line you'd expect without any free parameters. So it seems like the mode temperature of this oscillator is tracking the material temperature of the liquid helium, at least over the temperature range that we can access so far, and down to a mean phonon number of about 10. Okay, so that's everything that I wanted to tell you about. I would just quickly mention that even though this is a sort of outlandish optomechanical device by the standards of the field, the performance in terms of dimensionless figures of merit is very much in line with the state of the art of the present field. But there are a lot of aspects of the technical details that make us like this device an awful lot. Our hope, we have one idea for improving this mechanical Q, which is sadly kind of limiting us from doing some real laser cooling to the ground states or doing interesting physics. Remember that at low temperatures, the mechanical Q is limited by the acoustic wave's ability to leak into the glass. There's just not much to stop it. So in a new round of devices, what we've had made are dielectric stacks that provide us the high reflectivity for optical wavelengths, And in addition, a couple of extra layers of the exact same materials, but quarter wavelength for the acoustic waves now. So this should provide a high reflectivity mirror for the acoustic waves, and if nature is kind, this would give us an estimated quality factor of several million. So we don't know yet what devices are fabricated yet, but we haven't really measured them. Hopefully that'll make these devices even more competitive. As it is, they're just reproducing, they're just realizing regular old optomechanics. But when you've built something out of liquid that has always been built out of solid, there are probably some other possibilities. So some of the things that we're thinking about are taking the cavity and only filling it up halfway, and looking at optomechanical interactions with the free surface of the superfluid. There's some interesting molecules that can live in superfluid helium without damping and that have nice cycling transitions in the near infrared. It might be possible to introduce vortex lines into the liquid helium via turbulent counterflow, and if those vortex lines end up getting pinned at the surface of the cavity mirrors and overlapping with the optical mode, reading out the motion of the vortex lines with this optical cavity. Turns out that the mechanical properties of vortex lines in superfluid helium are still not very well understood, even though they play a fundamental role in things like superfluid turbulence and other basic fluid mechanics questions. Okay, so with that, let me thank the folks in my group, including 2 former postdocs who started these projects, the students here whose underlines in its color-coded fashion, our funding agencies, and thanks very much for listening. I don't know. I have no idea. My only way for thinking about generating this would be to have a heater somewhere, a heat sink somewhere else, and when you turn on the heat and there's a counterflow of normal fluid against the superfluid, generating some turbulence, but I just don't know. It's a small, obviously it's a small system, which is bad in terms of Reynolds number.
It's going to be small too.
Fair enough.
So how much higher do you expect the Q? I don't know if you mentioned that after you add the acoustic wave Bragg.
Yeah, the acoustic Bragg reflectors. If you just do the usual, boundary condition matching the mechanical properties of silica and tantalum, just adding 2 pairs would push the mechanical quality factor up to 10 to the 7, if it works.
Does helium-3 give you anticipation on the system at all?
Yes, so at these temperatures, helium-3 would have the viscosity of water. And when you linearize Navier-Stokes equation, that viscosity would turn into a damping term in your wave equation. So all this would be very low, very, very high damping. If you were willing to try this with superfluid helium-3 below 1 millikelvin in like a nuclear demagnetization refrigerator, I imagine there might be all kinds of exotic physics, but I think that's very impractical. These are optical cavities. Just to give a sense of the scale, in the membrane in the middle experiments, the circulating power inside of that cavity inside the cryostat is about 1 watt. So the fact that these mechanical oscillators don't heat up is really a tribute to the fact they're extremely good dielectrics at these wavelengths. And the fact that the whole fridge heats up a little bit is a result of the fact that some of that light gets scattered out into 4 pi and gets absorbed by metal parts. I don't think that's going to work at 1 millikelvin. But if we could get around that, I imagine there might be any amount of fascinating physics to look at with superfluid helium.
But you could dope with helium-3, and that might actually play a role in your vortices, right? Imagine having a small dope in helium-3, and the helium-3 would interact with the vortices in a different way than...
Yeah. That would certainly be interesting. The helium-3 dopants in the superfluid act as a gas. They act like as a dissipative gas. But at these frequencies, it's pretty forgiving. So for example, we don't have to use we don't have to do isotopic purification. The natural part per million of helium-3 doesn't add any appreciable mechanical damping.
So have you added helium-3 to verify that?
Think about it, things to do. We're trying to push Q up.
No.
Just change the direction.
Yeah, But one thing I would just point out is just to address your question, did we add helium-3 to see whether it's varying or not? This is the mechanical quality factor as a function of device temperature. This is the sort of no free parameters fit. I would say this is very rare in mechanical oscillators. In the whole MEMS community, you make the device and you measure Q, and you just don't ask too many questions. But here, you can actually calculate it basically from first principles.
Okay, that's okay. Yeah.
So there are kind of realist perspectives to push it to a strong coupling regime. How far are you?
Not in any of these devices. No. So I think there's a lot of interesting physics to do without them. There's some clever ideas about putting some of the nonlinearity in the measurement to get away from the sort of endless Gaussian quantum state physics. But these devices I don't see getting into the single quantum strong coupling. We have some other ideas about very different, qualitatively different devices that might do that, but nothing in what I talked about here.
I had a question about the data on your membrane quantum mechanics, where you compared the cooling and side bands as a function of the cooling. I had the impression that there was another mode coming in, and I was wondering whether there's some physical meaning to it.
There is, and it's that's light. So the light, what we're doing is we're monitoring the phase shift of light that's reflected from the cavity. And mostly we would like that phase shift to be due to the membrane's motion. But in reality, if the cavity stretches, if the mirrors fluctuate, and they all have thermal motion, all that motion gets imprinted on the light coming out. So in all of these experiments, when you first take data, you will see a forest of peaks associated with all these mechanical modes. The properties of the membrane are so well known that we know what its resonant frequencies are going to be. We can pick those out right away. But if you want to be extra careful, what we do anyway, you set some laser light in there, and this, the titanium block that we bolt the mirrors to just doesn't care about radiation pressure. Its modes will not be laser cooled, they will not be damped. Whereas the membrane modes go as soon as you turn on some laser power. So this is replotting the same data. This is the membrane's mode here. This is something that we see, but as we crank up the cooling power, the membrane mode gets strongly damped and strongly smushed, and this noise peak stays exactly the same. So this is just a normal mode of the spacer that gets transduced by the light in the same way. And in all these experiments, this is just sort of a fact of life. And when you build the device, you just kind of cross your fingers that the normal modes of the spacer don't overlap with all of your useful mechanical modes. Sometimes that happens.
When you cool one mechanical mode, what happens to it before now in the other mode?
Basically nothing. So there's this funny way of thinking about the Q of an oscillator as representing its thermal resistance. So high Q oscillator is only weakly coupled to the thermal bath, which is to say it's only weakly coupled. What high Q means is that the mechanical oscillator is only weakly coupled to anything else. That includes thermal fluctuations. So if I take, and you know this because if you take a ruler and you hold it down on your desk and you go like that, and you put some huge number of phonons in it, that relaxes back down to its Brownian motion on the mechanical ring down time scale. Likewise, if you were to clamp it shut and remove all of its Brownian motion and let it go, it would bring back up to thermal motion on its ring up time. And so if you think about that as being the rate at which 1/2 kT is being restored from the bath into your system of interest through a thermal resistance, that's set by Q. Yeah, so if you were to glue a thermometer to this device, it would not see anything getting colder. Another way of saying it is that these temperatures are achieved with a cooling power of about 10 to the minus 20 watts, which is a lot if you're only cooling 1 degree of freedom, but not much if you want to keep your beer colder.
If I add more lasers,
Yeah. Well, how many lasers do you have? Because it's you have 1 degree of freedom, 3 degrees of freedom for every atom in this object. So this is not bulk refrigeration. This is not going to keep your laptop cold. This is for isolating one normal mode of a big continuous object and studying the quantum physics of it as an isolated oscillator.
So I have one last question.
Okay.
With the HE2 star, can you produce enough of it to actually change the effective index of refraction?
No, so I think with the HE2 star, the idea would be that you would design your cavity to operate at 908 nanometers at the cycling transition. So be in the sort of nearly resonant atom cavity QED kind of setup.
Okay. And you thought about magnetically tracking the HE2 star?
No, I think it would be pretty well trapped by the density inside the cavity.
Okay, let's thank Jack again.